So on number 9, in order to have reflectional symmetry, we would need to be able to draw a line and the figure look identical on either side of that line. So you get your pencil out and you can play with it. You draw your good old vertical line. Oh my goodness, it definitely doesn't look the same on either side. You can draw yourself a kind of fancy diagonal line, but I still can't get it to look identical on either side of the line. Another clue is that there's an odd number of parts here, so it's going to be hard for it to have reflectional with those odd number of parts. So reflectional, no, so we don't say how many. It will definitely have rotational symmetry, because if you look at moving it in a circular motion, if I moved it in a circular motion, when I rotate it, that star will land on that star, kind of his spur, if you were wearing cowboy boots. And that one would land on that one, and then move you back to the beginning. So it does have circular rotational symmetry. So that one's a yes. And then we know always to find the degrees of rotation, we take 360, and then we divide it by how many congruent parts there are. There are 3 matching parts in this figure. 3. So we take 360, divide it by our 3 matching parts. So what I'm saying here is if I rotate this figure 120 degrees, it's going to look exactly like how it started. Then you add it to itself. Yeah, 120 plus 120, 120 times 2. If I rotate this, if I start at A and I rotate it 240 degrees, the figure will look exactly how it started. And then no, you do not write 360 because that's never a degree of rotation. So this one only has 2 degrees of rotation, even though you can rotate it 3 times, kind of. It has 3 congruent parts. If a figure only looks like itself when you rotate it 360 degrees, it has no rotational symmetry, because then every figure in the whole world would have rotational symmetry. Any figure, if you rotate it 360 degrees, looks like it started.